Just as the two-dimensional plane can be described using either rectangular coordinates or polar coordinates, we have multiple ways of describing three-dimensional space. In this video, we're going to focus on cylindrical coordinates, and in the next video, we'll discuss spherical coordinates. Cylindrical coordinates are what you get if you take polar coordinates and just drag it up into 3 dimensions. The core shapes that we get are cylinders, which is where the name comes from. The z-dimension is the same as the z-dimension in rectangular coordinates, and so the equations going back and forth between the two coordinate systems is basically unchanged from before. To go from rectangular coordinates to cylindrical coordinates, we use the relationships r equals the square root of x squared plus y squared, and tangent theta equals y over x, and then leave the z value unchanged. To go from cylindrical to rectangular, we use x equals r cosine theta, y equals r sine theta, and the z is unchanged. Setting up a triple integral in cylindrical coordinates requires us to get the volume element dv in terms of the variables r, theta, and z. Fortunately, we can use a general property of volumes to calculate dv. When you have a shape where the volume is created with constant cross-sections, then the volume is the area of the cross-section multiplied by the thickness. We know the cross-sectional area from polar coordinate integrals, so we multiply that by dz to get that the volume element is r dr d theta dz. This allows us to immediately write down the triple integral in cylindrical coordinates. The limits of the integral follow the same pattern as before by always working from lower to upper. The z direction is often integrated first, which then leads to creating an area in the xy plane, which can be broken down using polar coordinates. In these problems, you usually go back and forth between cylindrical and rectangular coordinates using the relationship r squared equals x squared plus y squared. It's worth taking a moment to look at a couple basic shapes described in cylindrical coordinates. All of these shapes are rotationally symmetric around the z-axis. You basically take the shape of a graph and rotate it around the z-axis to get these volumes. This makes sense because cylindrical coordinates are built around that type of rotation. The equation z equals r gives us an inverted cone that goes out at a 45-degree angle from the origin. If we let r be both positive and negative, we get a double cone. In general, lines will lead to cones. If the slope of the line changes, then that will be reflected in the shape of the cone. And shifting the y-intercept will change the location of the tip of the cone. The best strategy is to graph the line in the plane and think about what you get when you rotate it around the z-axis. Another common shape in cylindrical coordinates are paraboloids. These are equations that look something like z equals ar squared for some constant a. The constant a just adjusts how wide or narrow the paraboloid will be, and if the constant is negative, then the paraboloid will open downward. If you add or subtract a constant, you will shift the location of the vertex. These two basic examples formed the foundation of your intuition for graphs in cylindrical coordinates. Remember that these graphs are taking advantage of the fact that these are symmetric about the z-axis. Shapes that don't satisfy that property can be much more difficult to graph in this coordinate system. In the next video, we're going to look at spherical coordinates.